In this video, we're going to be talking about the forces acting in lifts. Now, in a lift, there's quite a few forces acting, and there's two different perspectives we can take. We can either look at the lift as a whole, where the tension in the cable is acting upwards, and the combined weight of the lift itself and everything inside is acting downwards. Alternatively, we can look at what's happening inside the lift, where we have the person or the object providing a weight downwards onto the floor, and then upwards the reaction force that the floor exerts on the person. Now, depending on the motion of the lift, these forces may or may not be balanced, and this is what we're going to investigate. Here's some little ideas that we're going to need along the way. The weight of any object is its mass multiplied by the acceleration due to gravity, which is 9.8. As well as this, we're going to need the resultant force, which is what we get when we add several forces together. In a lift, the forces are acting in opposite directions, so we are typically going to be subtracting these forces from one another. Let's talk about some of the simpler situations first. If the lift isn't moving at all, then the forces will be in equilibrium. This means that in the big picture, the tension will be equal to the combined weight, and over here, the reaction will be equal to the person's weight. Similarly, if the lift is moving but at a constant speed, then that still implies there's no acceleration and the forces will still be balanced. If the forces are not balanced, we will see some acceleration. For example, if we increased tension to be greater than the combined weight, we would see the object moving upwards. The way we would set this problem up is we would still write F equals ma, but within F, we would include both of our forces and consider the resultant. Now, since tension is acting upwards in the direction of motion, and weight is acting downwards in the opposite direction, what we'll do is we'll consider tension to be a positive quantity, and we'll consider the weight to be a negative one. So our F equals ma becomes tension minus weight equals ma. The same principles apply for the zoomed in version. So if the direction of motion and the direction of acceleration is upwards, we could set up the problem as the reaction minus the person's weight. And if the direction of motion is downwards, we can just reverse the direction of both of these forces. Here's an example from the WJEC's Mechanics 1 paper from 2014. We've got a crate of mass 25 kilograms resting on the floor of the lift, which is descending. The direction of motion is going downwards. We're going to try and find the reaction force initially when the acceleration is 1.2 meters per second squared. And then in part B, we're going to try and find it when the velocity is constant. So what we'll do is we'll try and find some of these other forces. Because we're given a mass, we can determine that the weight of the object is given by 25 times 9.8, which is 245 newtons acting downwards. We've replaced that here. Now, if I think about F equals ma, because the direction of motion is downwards, I want 245 to be a positive quantity, and I want r to be a negative quantity since it's going upwards. I'm going to substitute in what I know into this equation, which is a, m, and w. And at this point, the only thing that I do not know is the reaction force R. If I rearrange the equation, I should be able to get the answer out as 250 newtons. Now, in part B, the velocity of the lift is constant. So we are disregarding this previous A value, and we're now considering a situation where the acceleration is 0. If the acceleration is 0, it means our forces are balanced. So in this second case, the reaction and the weight are equal, and the reaction will work out as 245. If you want to see a few more examples involving forces in lifts, click on the link which will take you to a separate YouTube video.